Hey everyone, I'm Nick, and I'm a performance engineer and computer architect at the Silicon Valley startup Cerebras Systems, where we make the world's largest chip, the wafer scale engine, and I'm very happy to be here today to talk about the programming language C++ and give a bit of a crash course on the subject. So I've worked with C++ for a number of years. At this point, mainly in the domains of microarchitecture simulators and high-performance software. And it's a language that I find to be very interesting for two main reasons. So for one, I think it's a very interesting language because it's used almost everywhere. So you can find C++ in game engines, you can find it in machine learning frameworks, you can find it in high-performance software, in physics simulations. So it's doing almost anything, and it's almost everywhere. And the second reason why I find it to be very interesting is the development of C++ over the years and over the past few decades, and how much the language has grown and changed. So most recently we had the C++ 20 release, and with it came a number of great changes to the language and to the supporting libraries that really changed the way that we write C++. Okay, so now we have, before we actually get started looking at all these examples that I've written, we should talk a little bit about the language. So C++ is a compiled language, meaning that we don't directly run our C++ code. We have to first pass it to a compiler that will translate it into the machine code in the form of an executable that we can actually run. So the compiler may change from system to system, or operating system to operating system. So if you're on Windows, you might be using MSVC. I'm on Linux, I'll be using GCC today. You may also be using Clang if you're on Linux or on a Mac. So a whole bunch of different compilers to choose from, right? That all have the same goal of translating your high-level source code into that machine code that will run on your processor. A second thing to note about C++ is that it's a statically typed language, meaning that with the variables that we work with, we assign these variables a type. Type might be something like an integer or floating point number, or it might even be a class that we've defined, or maybe a class that's a part of the standard template library. But once we've assigned a class, right, to a variable, or a variable we've initialized or defined using a particular class, that's a fixed thing at compile time, so that can't be changed at runtime. Okay, so kind of digging into this idea of what is the core of C++, let's dig into the first example, right, which is this example 0, this main.cpp. And we have a couple important things to note here. First of all, comments, right? So in C++, we use these two slashes to denote this line is commented, or everything after these two slashes is a comment. Comments are completely ignored by the compiler. They don't affect functionality whatsoever. They're stripped out by the compiler completely ignored. But they do serve a very important role in terms of documentation, especially when you start working on very large projects with multiple collaborators, right? It's very important that you keep track of what your code is doing. That way, you don't look back at it in 6 months, or a new coworker doesn't come to look at it and have no idea what's going on. So it's a good idea to comment your code. The second thing we have inside of this main.cpp is a main function, and this is very important because this is the core of every C++ program. Every C++ program has a main function. Right? Why does every C++ program have a main function? Well, the main function is special in that it serves as the entry point for execution. So whenever you run a C++ program, where does it start executing? Well, it starts execution logically at the main function, right? Now the main function is really just a function that acts in this kind of special way, but functions have 4 key parts. They have a return type. In this case, it's an integer, so basically a positive or negative whole number. It has a name. In this case, it's main. It has a list of parameters, so the things that we're going to pass into the function. Main, very specifically, has 2 signatures, one with 2 parameters, one with 0 parameters. We're going to be using the 0 parameter version for these examples. And then it has a function body. So this is where all our code goes that we're going to execute. So we might create variables in here, call functions, create classes, all manner of things. So in this case, we'll be doing the most simple main function we can do, one that does absolutely nothing except return 0. So the integer that we're returning from this function is going to be 0. And very specially, the return code from main is going to signify how the program exited. So whether or not it exited successfully, or maybe what kind of error code it returned. So 0 signifies that we exited successfully. Okay, so let's go ahead and quit out of here, and let's compile this and run it. So we can compile it. In my case, I'll be using GCC and the compiler driver G++. So to G++, I'll just pass my source code, which will be this main.cpp, and I can give it an output name if I want. So maybe I'll call this main.out. And we can see here, we now have an executable called main.out. Now I can run main.out by doing /main.out, and as you may have suspected, we have the very exciting nothing happened, right? We wrote a main function that does nothing but return 0. But we can actually see that value 0 by doing echo $question mark. Right? That'll show us the return code from our last command. And if we actually go in and change that in our main.cpp, right, we change this to say, instead of being 0, maybe it's 127. Remember, we have to recompile this, right, if we make changes to our source code, because it is a compiled language. And we run this again, and then do that echo thing. We can see we now see 127 now, right? So that just gets plumbed all the way through. And that's our return code. That's how our program exited. So this is saying we've got a return code of 127 from our program. Okay, cool stuff. So let's go ahead and get rid of main.out. And we can continue on by looking at the classical first program that most people learn when learning a new language, which is going to be a hello world program. So, you know, when writing kind of any code, it's very important that we don't reinvent the wheel, and we use things that are part of the standard libraries for our language. And so one of these libraries, of course, is going to be libraries for I/O, or input and output. Now for C++, we have a few options. We can use the C library, stdio, or we can use the IOStream library, which is for C++. So in this case, we'll be using the IOStream library because we're writing C++ and focusing on how we do things and, you know, more idiomatically in C++. So here I have a directive include that's saying to the preprocessor, all right, of GCC to go fetch the files that I need for IOStream, right? This IOStream library. So this is just going to tell the preprocessor part of the GCC to go fetch these files and paste it right here in my program. So after I've included those, I can use them throughout my code in different functions and inside of my main function in this case. And the specific thing that I'm going to be using is this coutstream object, right? So one thing you might notice here is this std : right, or std : now C++ has this thing called namespace, which is very important for large projects where you may have duplicate names, right? If you've written 10,000, 100,000 functions or something that is part of a big library or multiple libraries that are kind of coming together, it's very likely that a name gets reused somewhere. So one way we can avoid these naming conflicts is by using these things called namespaces. So namespace just allows us to wrap all of the functions for, say, a particular library into one unified namespace. So in the case of the C++ standard library, all of the C++ standard library lives in the standard namespace. So when we're using cout from the standard namespace, we use std : cout, which is saying I want to use cout from the standard namespace, where this : is what's known as the scope resolution operator. So I'm using cout from the standard library. Okay, so to actually print out to cout, we're going to pass using this less than this string, hello world, and a new line character So it prints on a new line. Okay, so let's go ahead and exit out of here, and we'll compile our Hello World program. And we can call this the output executable, something like Hello World. And then we see our executable there, and we can run it, and we can see that it prints Hello World to the screen. So another nice thing about the cout stream object is we can actually chain these less than operators. So, for example, I could do something like this. So I could print out Hello World, then print out a new line character, and I can keep these different prints on the same line. One perhaps thing to note here is that double quotes and single quotes do mean different things in C++ as compared to C. So single quotes are for single characters. Double quotes are for one or more characters, or zero characters. You can have 0 characters in there as well, an empty string. Okay, so let's go ahead and compile this, and we see that we get, when we run it, functionally the same thing, right? But we can chain those operators together to print multiple different things. Okay, let's go ahead and revert that and move on to the next example, right? And we'll get rid of this Hello World executable as well. So oftentimes you want to do even more interesting things than just printing out Hello World. We often want to store some state, right? We want to keep things in variables. So let's go ahead and open up our variables example, example 2. So when we're working with variables, variables have kind of 2 main parts. We have the declaration of the variable, and then we have the initialization of the variable and any uses of those variables. So when we're declaring a variable, we declare a variable with a type and a name. Those are at least those 2 things. We can also initialize it on the same line, but we at least need the type and the name. So here we have a declaration of 3 different variables, A, B, and C, that are all integers. And what does this fundamentally mean to the compiler? Well, what we're really doing here is we're just asking the compiler for a few pieces of memory. We're asking it for a piece of memory to store A, or an integer that we're going to call A. We're asking the compiler for a space of memory to store an integer that we're going to refer to as B, and the same thing for C, right? So we're just asking the compiler for a little bit of memory, right? Enough to store an integer. Then down here, we can actually initialize, right, this memory. So I can set A to 5, right? So I can set that piece of memory to be the value 5, represented as an integer. Same thing with B, and then the same thing with C. I can even set it to, A plus B if I wanted to. So I can use operators on my my other variables here and set C equal to be the result of this expression on the right-hand side. Okay, so that's one way we can do things, and you can see we're using std_cout again to print things. Print out A plus B is equal to the result, should be 15 in this case. And down here we see a bit more safe way of doing this, or the more preferred way of working with variables, which is where we initialize and declare the variable on the same line. Right? So here we're creating a float D and initializing it to 5.5. Here we're creating a floating point number E and initializing it to 10.3. Right? And the same thing, F, setting it equal to D plus E. Right? So why do we typically prefer this form of declaring and initializing on the same line? Well, it's much easier to prevent using uninitialized memory if you are always initializing when you declare something. So up here, there may be a case where I declare a whole bunch of variables, and then I'm using them later on in my code that I'm writing, and maybe I forgot to initialize something right at the very top of my program, and I'm 100 lines down. So that can lead to problems because you may just be reading garbage data from a variable that hasn't been initialized yet, versus the case where we're always declaring and initializing, where we prevent that from happening. Okay, so let's go ahead and compile this. So we'll compile this o2 variables.cpp, and we can see we get kind of our expected results here, but now we're storing some things in memory. Okay. One other very interesting thing to note here is this really cool part of C++, which is called automatic type deduction. So instead of float here, I can use the keyword auto. And what auto means in this context is that we're allowing the compiler to deduce the types of these variables for us. So how exactly, or roughly how does your compiler do this? Well, it does this by looking at what's on the right-hand side here. So in this case of D, it sees that we have a floating point number on the right-hand side. So it's going to make D a float, right? And the same thing for E, and the same thing for F, right? It sees that the right-hand side is the result of the sum of two floating point numbers, which is going to be a floating point number, right? So it's able to deduce that type as well. What we can't do is just declare something with an automatic type, right? Like we said kind of at the beginning of this talk, C++ is a statically typed language, which means the compiler has to know what the type is at compile time, right? It can't be a runtime thing. So automatic type deduction requires this as well. But we see that, if we sub out float for auto, right, and we recompile our program, and we run it again, we get the exact same result. And this auto, while it may not seem very useful in this particular case, it can be very useful, especially when you're working with types that have very long names, like some of the standard library containers. So it's what we typically call syntactic sugar, right? It's a way that we can write C++ easier, but it doesn't really have an effect on anything else. It's just a way we can more easily write our code and maybe be more expressive about what we're writing. Okay, so let's go ahead and quit out of here, and we'll move on to some of the other core parts of the language. So another thing we have is this idea of control flow. So we'll open up control flow. So we don't always want to execute every single line inside of our programs. Sometimes we want to selectively execute code, and we can do that with if statements and else statements, right? So in this case, we'll create two variables, integer a, set it to 5, and integer b, and set it to 10. And then down here, we'll have if and else statements. So we'll have the form of an if statement is we're going to execute some code if some statement is true or some expression is true. So if a is less than b, we're going to execute this print right here. Otherwise, right? So else, we're going to check this next condition. So else, we're going to check if a is equal to b. If that's true, we'll go ahead and execute whatever's in this scope, right, within this these curly braces. And then finally, right, if that's not true, we'll execute what's in this else side right here. So this is kind of our catch-all, right? So if we didn't execute either of these, everyone else will fall into this else, where we print out a is greater than b. Right? And very importantly, only one of these will ever be executed, right? So if a less than b is true, we'll execute this print. If a is equal to b is true, we'll execute this print, but neither of the others. And if neither of these are true, these first two are true, we'll end up executing this else statement. So in this case, a is less than b, so we should print out a is less than b. Okay, so let's go ahead and compile this O3 controlflow.cpp, and we'll go ahead and print this, and sure enough, we get the expected result. And if we go ahead and change this around, say for these two values to be equal, say for both of them to be 10, and we go ahead and compile this, we see we get the expected result as well. We executed that middle one, where a is equal to b. Okay, so let's go ahead and quit out of here, and we'll continue on with our examples. And we'll talk a little bit about loops. So we don't always just want to execute something one time or two times or three times. There'll be cases where we want to execute things, maybe the same few lines of code, for 100 times, 1,000 times, 1,000,000 times, or maybe forever, right? We might have something that's just supposed to be always awake and constantly reading data and processing something. So we need loops for this. So in this case, we'll start out by looking at for loops. So we'll go ahead and open up this for loops example. And we'll look at a for loop that's very similar, or pretty much exactly how we'd write it in C, right? So here we have a loop, a for loop in this case. And our for loop has three major things. We have an initialization, we have a condition that we check, and then we have what we do at the end of each loop, right? So the first thing that we're going to do is we're initializing some value, some loop counter usually. So we're setting this integer I equal to 0. Then on every single iteration of the loop, we're going to check, is I less than 10? That's going to determine whether or not we stay in the loop, right? If I is less than 10, we stay in the loop. If I is not less than 10, we break out of the loop. And then at the end of each loop, in this case, we're going to increment I. So this I++ is the same thing of saying, or same way of saying I is equal to I plus 1. In this case, this is a post increment. There's also a pre-increment with some subtle differences between the two. So what are we doing here? So we're just going to run this loop for 10 iterations, counting up from 0 to 9. And we're going to print out each of those values and then a new line character. Okay, so let's go ahead and try this out. So we'll compile 04 loops.cbp, and we'll go ahead and run this. And we see we get 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now the way to kind of read this, if I'm reading this for loop trying to understand what's going on, I would say something like, for I is equal to 0, while I is less than 10, increment I, and I'll be doing whatever's in this loop for that number of iterations. Okay, so we'll go ahead and quit out of there, get rid of that executable, and we'll move on to our second kind of loops, which are these while loops. So while loops we can use in much the same way as we do for loops. So we can have something like set some variable I is equal to 10 ahead of time, and then I can say while I is not equal to 0. Right? So these can be useful if we don't say have a set value that I is going to increment or decrement by every single iteration. And it might vary, right? And it can't be captured by a single statement like I++ or I minus minus. So while loops are useful in that regard. In this case, we could do the exact same thing with either a for loop or a while loop. So it doesn't really matter in this case, though. So here, what are we doing? We're just going to set a variable I is equal to 10. We're going to run this loop while I is not equal to 0. We'll print out the value of I, and then we'll decrement it. So just like we have that post increment, we also have a post decrement, which is the same thing as writing I is equal to I minus 1, with a few caveats there. And then print a new line character out. Okay, so there's our basic while loop. And let's go ahead and compile this. It's while loops.cpp. And we'll go ahead and run it. And we see we get what we expect, right? So it counts down from 10 to 9, 8, 7, 6, 5, 4, 3, 2, 1. That very last iteration, it decrements from 1 to 0. When we get to the top of the loop, go ahead and open that up again. When it gets to the top of the loop, it sees that I is now 0. It checks I is not equal to 0. All right, so in this case, it would say 0 is not equal to 0 when I is 0. So this would be false. So we break out of this loop, print out the new line character, and return from main, right? Return 0. Okay, so there's our basic while loops. So let's continue on, get to another core part of the language, which is going to be functions, right? So in many cases, when we're writing programs, we'll have code that gets reused over and over again. Now, while we could write those lines of code 10, 20, 30, 40, 50 times, that can be pretty wasteful, right? So what we can do instead is we can write our own functions. So just like we have a main function here, we can write our own functions that follow the same format. So we have a return type, a name, a list of parameters, and then a function body. So in this case, we're going to write a function called square. So let's say we want to square a number, just multiply it by itself. So in this case, we're going to take in some value that we want to square, an integer, and then we're going to return the value multiplied by itself, right? And we can call that inside of our code as we see here. So we'll create a value called result, or a variable called result that's an integer. And we can invoke this function by calling square with some argument. In this case, that argument is 5. So 5 will be copied into this variable val here. And then we get returned from that 5 times 5, which result gets set equal to the value of. Should be 25. And then we'll go ahead and print out the result. So this is an example of what we call pass by value. So we're passing this value of 5 into this function here. We could also pass a variable that's an integer into this function. It would work just the same way. But here we're doing pass by value, which means we're copying whatever value we're passing in as an argument into this variable and then returning something. Okay, so let's go ahead and see if this works. So it should print out 5 squared is equal to our result, which should be 25. So let's go ahead and quit. We'll compile 06 functions.cpp. And what do we get? We get the expected result of 5 squared is equal to 25. Okay, really great. Okay, so, just like we saw how that might be useful in terms of maybe we have a very complicated function that I don't want to duplicate the code for over and over again. Instead of duplicating that code, I can have a function and just call the function, right? And duplicate calls, right? Instead of the entire function. So just like we can save there in terms of how much extra code we have to write. Another way we can save the amount of code we have to write is by having the compiler generate the code we need for us. And we can do this with templates. So let's go ahead and open up our next example, which is this templates.cpp. And we'll be looking at function templates in this case. So let's say we have a function that we want to make more generic, right? Maybe we know we're going to need multiple versions of these functions that take different types. And I don't want to have to copy this function 10 times, 20 times, 30 times, depending on the type. So instead of doing that, I can templatize the function. So I can have another parameter for this function, which is a type. So here I'm going to say template, type name t, above our function. In this case, it's square. And what we're going to do here is instead of returning, say, an int or a float, it's going to return whatever this template type is, right? So here, it's going to return something that's a t and take in a value that's a t, and we're going to return that value multiplied by itself. Now, templates are purely a code generation tool. We're just telling the compiler to generate versions of this function based upon whatever type we need. So in this case, we're going to do basically the exact same thing that we did in the last example of functions, but now we're going to use templates for the type int here. So we'll call our function with an int, and we'll give it the we'll instantiate this template with type int, so that'll be our type t, and we'll do another version of this template using this type float here. So we're basically offloading the work of creating these functions to the compiler. So the compiler will generate the code for a square function for the type float automatically for us. So let's go ahead and make sure that this works. We're going to square the integer 5 and also square the floating point number, 5.5. And we'll make sure that this works. So we'll compile 07 templates.cpp. And we'll run a.out, and we get the right result. So 5 squared is 25 still. 5.5 squared is 30.25. Right? So this is really great. We have a way that the language and the compiler are helping us out and keeping us from having to write unnecessary code. Right? We're offloading the work of writing that code off to the compiler. Right? The compiler is generating it for us. Okay, so that's a little bit on templates. There's, of course, much more that we could go into. So now that we've talked a little bit about templates, we should dig into what's known as the standard template library. Right? And this is the C++ library that contains templatized containers, right? And data structures, as well as templatized algorithms. So the first thing we'll look at is one of very important containers, maybe the most used containers in the STL, which is the vector. So we'll open up this vectors. So here, we're going to include something new for the first time. So we're still using the IOStream library for printing, but we're also going to include std vector, right? Now, a vector is a linear container, so it's like an array, but it's not fixed size. It's dynamically sized, so it can grow and it can shrink as we need it to. And so here we're going to create a std vector, and it is templatized. It's from the standard template library. So we're going to use a std vector of integers. So let's say we wanted to have a dynamically sized array of integers. So we'll have a std vector of integers, and we'll call it v. Right, that'll be our vector. So we'll have a for loop here. We'll say fill it with some numbers. So here we'll do that same for loop that we saw in the past. We'll go from I is equal to 0, while I is less than 10, increment I, and we'll just store the values of I in our vector. Right, and we'll do it with this pushback method. Right, so a method is like a function, but it's tied to a class or a struct. So vector implements a method called pushback. And what this pushback method does is it will insert a new element at the end of the vector, right? And it will grow the size of the vector if it needs to. So it might need to do a dynamic allocation to grow the amount of memory, or the size of the allocation that this vector is using to store the data. But it will all be handled for you. So we don't need to spend the effort to implement our own dynamically sized array. We can just use one from the standard template library. Okay, so we filled up our vector here with the values of I that we saw in our for loop. And then down here, we'll use a for loop to just print the contents of a vector. And we're going to use a slightly different for loop here than we've seen in the past. This is what's known as a range-based for loop, and this is where we start to depart from the C style of things. So not only do we have STL containers like std vector, we also have very nice for loops that we can use with those containers. So much like in Python, you can write, when you're working with a list or a dictionary, you can say, for I in list, right, to automatically unpack the contents of that list into that variable I. We can do, a very similar thing in C++ with these range-based for loops. So I can say for integer I, and then colon, this is our in v. So for our integers in our vector, we want to just print out that integer. So we have a way of just iterating through that entire container and unpacking the values without having to do anything like indexing, and which is often prone to errors, such as indexing out of bounds. So if my vector only has 10 elements and I access element 11, that can cause an error, right? And your program can crash. So this is a very easy way we can get around that in C++ and prevent that from ever being a possibility, because this will always go through the contents of the vector, and it will never go out of bounds, guaranteed to never go out of bounds. So there's our range-based for loops, and we can use this with, I believe, all of the STL containers. And you can find here on the CPP reference site, you can find a list of all the different kinds of containers we have, from fixed size arrays to lists, so linked lists. And there's also hash table implementations in here as well with these unordered maps. Okay, so let's go ahead and compile this. So all we're doing is we're pushing back some values into our vector, and then we're printing the contents of the vector. So we'll go ahead and compile that, and we'll run it, and we see we get the contents of our vector, which are the numbers 0 to 9. Right, very cool. All right, so let's go ahead and get rid of that, and let's look at another part of the standard template library. So I said the standard template library has two really great parts. One of them is all the containers that we can use right out of the box. Another thing that we can use is the algorithms that work really well with these containers. So let's go ahead and look at the algorithm side of things. So we'll look at algorithms. So here, let's say we want to sort our vector, right? So here we'll create a vector of integers, and I'll just initialize it with some values. So 10, 24, 1, 5, 16. So no particular order. So, a very easy way we can sort this without having to write our own sorting algorithms is by using those implemented in the STL. So another new header to include. So here I'll use this include directive with algorithm. So I can use the STL algorithms. And then specifically the algorithm I'm going to use is std sort, right? So this is going to sort one of our containers. And so we'll pass in the beginning and the end of our vector, which are these iterators. And we get that by calling the method begin on our vector and the method end on our vector. And that'll give us the range that this algorithm is going to sort over. So we don't need to sort the entire vector if we didn't want to. We could also sort part of the vector. But in this case, we'll just sort the entire vector. So we'll sort the vector from the beginning to the end. And then you see here, I've done a little helper function here, so I don't have to duplicate code. So we'll print the value of the vector ahead of time, and we'll print the value of the vector after we sort it. So what will end up happening here is we pass the vector to our function, it gets copied in, and then we print out the contents. So let's go ahead and quit here, and we'll compile algorithms.cpp, and we can see, we'll print out the vector before and after, and we see that we sorted the vector, right? And we didn't have to implement our own sorting algorithms either. And there's many other algorithms in here. So if we go to, say, the algorithms library and CPP reference, you can see there's a number, there's copy algorithms, there's transform algorithms, generate algorithms. We can reverse something, we can rotate and copy, we can partition a range of elements, right? All kinds of great things, including sorting. Okay, so that's a little bit on our algorithms. The next thing we have is this idea of references. So up until now, we've been mainly talking about functions, and I mentioned briefly this idea of pass by value. So here we'll look at a slightly different version, which will be pass by reference. Now, when we're doing pass by value, we're copying a value into a function. When we're doing something like pass by reference, we're just passing a reference to a value that already exists. So in this case, we'll be looking at that with this vector and this function called setVector. So setVector, instead of just taking a std vector of integers called v, we'll use ampersand to say that this is a reference. So instead of just taking a std vector of integers, it's going to take a reference to a std vector of integers. So this isn't going to be a new variable. It's just going to refer to this original vector that we're going to pass in. That way we don't have to do a copy of this vector into the function, right? And as you can imagine, pass by reference, it can be really good for performance. Say if you have, a giant data structure that's 20 megabytes. Well, you wouldn't want to have something that's 20 megabytes here, copy 20 megabytes in, and then return 20 megabytes maybe. Instead, you might want to just copy a reference to this 20 megabytes in, right? Basically just a memory location of that 20 megabytes, work on it, right? And then you've just modified what you originally had, didn't make any copies. So that's where pass by reference can be very useful. So in this case, we'll be using the setVector function to just push back some elements into our vector, and we'll go ahead and print it out here. But you'll notice the setting of those contents of the vector occurs in this function, but that works here because we're passing this vector in by reference. Okay, so we'll go ahead and quit out. We'll compile our references example, and we'll run it, and we see that our vector gets set within the function, and we don't have to return anything either. Right, so if we go ahead and open up references again, our function doesn't return anything. It has a return type of void, which means it doesn't return anything. But we're passing in a reference to our original vector, so that's how those values are being pushed back in, right? It doesn't need to copy anything back out. Okay, so there we have references, and we're reaching near the end of our examples. So it wouldn't be a C++ talk if we didn't talk about classes that we write ourselves at least a little bit. So here, the data structures and the types that we have available to us from the language in the libraries, it's not always enough. Sometimes we need custom types. And we can build our own custom types using structs and classes. So a class or a struct is just a way that we can tie data and the methods that work on those data together. So in this case, we'll do a simple example of a class called wallet. So wallet will have a couple data members, so dollars and cents, and just the contents of the wallet. And then it'll have some methods, right? Some functions that are associated with that data. So we can implement a print method that, say, prints the contents of the wallet. So it prints out dollars and cents. And then we might have a set dollars and set cents method to set how much money is in the wallet. And we have this private and public here, and these are access specifiers. It says who can access dollars and cents, right? So if we make something private, that means it has to be accessed by one of our class methods. It can't be accessed externally, say from within the main function. It can't be accessed from there. Public can be accessed from wherever, so we can call these methods from the main function if we wanted to. So let's see how we can do this. So just like any type, we can create an instance of this class, which will be an object, by saying wallet w. So we're creating something of type wallet, and we're going to give that the name w. Then we can call some of our public methods. So we'll set the dollars and set the cents. So we'll set our wallet to have $10 and 7 cents. And then we'll go ahead and call the print method, right? And that'll go ahead and print the contents of this wallet. And we can create as many wallets as we want, all with their own unique dollars and cents values. So let's go ahead and quit out of here, and we'll compile our classes example and go ahead and run this. And we can see that it prints out our wallet contains $10.07. So you can see how this can be incredibly useful when you need your own custom types that maybe do something special that isn't covered by things that are already in the containers library. Okay, so the last two examples that I have are on threads and locks. And I think those are kind of a special thing that are very useful to look at, especially if you're interested in performance. We have massively parallel processors today, both in terms of having our GPUs, of course, but even our CPUs have quite a number of cores these days, upwards of 8 or 16, or even stretching the limits to 32 cores. So it's important that we know how to write some simple multi-threaded code. And we can do that fairly easily in C++. So here, we'll write some very basic multi-threaded code. So we'll write a function called print. All it does is take a thread ID that we want to print out. And inside this function, we're just going to we're going to print using stdcout. We're going to say printing from thread, and then we'll print out the thread ID. Okay? Very simple function. We're going to be using threads, so we're going to import the thread library. So we'll include thread up here. We can actually also take this vector out while I'm at it. And we can launch threads fairly easily. So here, I'll create some std threads. These are variables, so we'll create a std thread t0, and we'll pass it the function that we want to launch with this thread. So in this case, we want to launch a function print and a thread ID of 0, right? So that's what this thread will print. Another thread, T1 will print 1, T2 will print 2, and T3 will print 3. And then down here, we'll wait for the threads to finish before we continue on any further. So we'll wait for thread 0, then 1, then 2, then 3. So we'll spawn all our threads off, wait for them all to come back and join them, and then return 0. It's very important that we put this join here, because otherwise we might spawn all the threads, and then your main function and entire program ends, and something crashes. So let's go ahead and see how this works. So we compile this threads.cpp. Now, whenever you're doing multi-threading, underlying this, it's going to be using some sort of thread library. So on my machine and on Linux machines, it'll typically be pthreads. So we'll need to link against libpthread, so -l pthread in my case. And you can see if I run this, right, I get kind of a funny output, right? Even though all those prints look like they were together, they're now getting interleaved in different ways because they're occurring in parallel. So, sometimes the result may seem sane like it is here. Other times, lines can get jumbled together. And that's because I have multiple things printing out to the screen at the same time, right? So, I can get different orderings and I can get different interleavings. Okay. So the final thing that I'll kind of show off is how we can kind of address that problem using locks. So we may not want multiple threads to be able to print at the same time, right? We may want threads to, print their entire string before someone else can try to print their entire string. And we can do this with a lock like a mutex, right? So we'll include another thing from the Mutex here. And you can find all of these things in, say, the thread support library on CPP reference if you want to learn more. So here we'll create a Mutex, stands for mutual exclusion. Make sure only one thread can access some shared resource, in this case, our printing the cout stream object at the same time. So what we're going to do is we're going to try and print. But before we try and print, we're going to grab the lock. Once one thread grabs the lock, it goes into the lock state. No one else can get it. We'll go ahead and print out our string, and then we'll unlock the thread so that some other thread can go ahead and get it. The rest of the code remains exactly the same, and we can go ahead and quit out. And we can compile 13 locks. Oops, got a link against libp thread again. And we can go ahead and run this. And we see that we no longer get the interleavings. We may get different orders for our threads. So, 0123, 0321, 2013, etc., but they're not interleaved anymore, right? Because we're using that synchronization mechanism. Okay, so that's going to go ahead and do it for all of the examples I have. Hopefully that gives you a little bit of the flavor of C++, and hopefully it shows you some of the differences and things you might not have expected if you're coming in from a C background or maybe a different language. But hopefully it's enough to give you kind of an entry point into the language, and hopefully you find it as interesting as I do. Great reference to look at is always cppreference.com. And of course, you can check out any of this code at github.com/coffeebeforearch/cpp tutorial 2021, right? We have all of this source code freely available, and I'd be more than happy to answer any questions. That's going to go ahead and do it for me. It's been great giving this talk, and feel free to reach out to me if you have anything else. Thanks a lot.